Okay, great, thanks. So, good morning. So, the title of the set of lecture is Spectrostatistics. Of random operators. So, let me add the remaining part of the title. In the localized regime. And, well, I'll start with a simple example to see what kind of results we want to get, okay? So it's based on work that is quite recent. Roughly, the spectrostatistics are things that have been derived in the last, 5 years, right? So it's recent material. The way what I'm going to present, of course, there's been work prior to, on these subjects prior to that. For some special models, but here we're going to develop a general theory. But I'll start with an example. And it's just the following thing. So take the following matrix. Let me call it, well, what did they call it in my notes? I didn't give it a name, actually. So take omega 1 on the diagonal, omega n. And off diagonal, you put first the lower and upper off diagonals are 1s. 0, right? So let me call this matrix Mn of omega. And what are the omegas? Let's say that the omega n's for n integers are IID random variables. So IID means independent and identically distributed, right? And assume, just for the sake of the example, assume uniform distribution on minus 1/2. Right? Assume you have uniform distribution on minus 1/2. Okay. And of course we have this, so they are real because they're distributed in minus 1/2, right? So we have a self-adjoint, a symmetric, real symmetric matrix. So we can look at the spectrum. Of Mn omega, which I will call E1, depends on omega, less than En omega, and I order them increasingly. Okay? Well, then we're going to prove a number of things, but we're going to prove the following theorem. First, for phi continuous, there exists nu, a measure, which is actually, so real, nu, a measure, well, actually in this case, I'm going to take it a function, actually. Nu is just a function which is positive valued. Such that, so it's going to be bounded such that for any phi continuous real valued, if you look at the following thing, you take 1 over n, the sum, so here there's this small n, okay, that's fine. Say the sum from k equals 1 to n of phi of ek omega. Well, this converges omega almost surely as n goes to infinity to the integral of phi of e nu of e dE. Right, so this is bounded almost surely, okay? Surely bounded function. So this is just 1 over n, the trace of the matrix phi of Mn of omega. Right? So this defines the function nu. Such a function nu exists, it's bounded, it's non-trivial, and the support of nu, one can show that support of nu for this matrix is exactly equal to minus 5 halves. Right? Actually, nu is supported exactly on this interval. Right? Okay. So that's not about the spacings. Actually, this thing is called the density of states. That's called the density of states. Of, well, of something which is not on the board, which is actually, I call it density of states. Okay. I don't say of what, but it's something which is not on the board. I don't want to put it on the board. I want to keep it with finite matrix. But I need the new for the next two statements. The second thing I'm going to do is the following thing. Pick E inside the support of nu. Let me call it E0. Right? I pick it inside the support of nu. And I do the following thing. Pick I1, Ik intervals, real intervals. Right, you take real intervals, so intervals of the real line. And you do the following thing. You look at the probability that the number, look at the, so I need, okay, and you pick integers, and you also pick integers, k, well, let me, m1 to mk, integers, right? And you look at the probability that for j going from 1 to k, there are exactly j eigenvalues of mn omega in the set, what is the set? E0 plus 1 over n, and I'm going to normalize, divided by nu of E0, right? By nu of E0 times ij. So let me draw a small picture. I'm going to draw the picture here. I do it for two intervals. I take k equals 2 for the picture. I have E0, and let's say, so this is, so we have the eigenvalues.
Where do we need mi?
There are exactly, not j, but mj, thanks. This is mj, right? I take mj eigenvalues, thanks. So let me put in blue the eigenvalues. So these are random numbers, right? These eigenvalues are random. And what I do is I take near E0, I take a small interval, right? So this is, I have one of these small intervals. So this is just the interval E0 plus 1 over n nu of E0. Nu of E0 is a fixed number times I2, for example. It's this interval. And here I have the other interval. Right. E0 plus 1 over n u of E0 times I1. Okay. So if you want, another way to say this is I take this picture of the spectrum and I blow it up. I multiply it by n times nu E0. I multiply the picture by n times nu E0. So in this new picture, right? So I do the following thing. I do the following transformation. X, or an energy E, gets transformed into E minus E0 times n times nu of E0, right? So E0 gets mapped to 0. This one. E0 gets mapped to 0. And this interval, of course, gets mapped to the interval I1. And this interval I2 gets mapped, so this gets mapped to I1. I2 gets mapped to, this small interval gets mapped to I2. And I count the number of eigenvalues right, of my random process sitting in there. Okay?
We don't require intervals ik to contain 0.
No. Ik are real intervals, and the only thing I ask is I want ik to be distinct from ij to be distinct from ij prime if j to be disjoint from ij prime if j is different from j prime. Right? I want them to be. Right? They don't need to contain 0. They can be anywhere, but I want them to be disjoint intervals. And then the theorem is the following, is that this probability, when n goes to infinity, converges to the product for j from 1 to k of e to the minus the length of ij to the power kj divided by kj factorial. That's the second statement. Meaning that the probability that any of these intervals, that all the intervals jointly contain, ij contains a kj, is given by this Poisson law, right? This is the fact, that's a thing that can be summed up as the local process of eigenvalues, meaning the eigenvalues once you rescale them in this way, right? What we did here is we did the following thing. We started with the eigenvalues and we defined the point process for k equals 1 to n, and you put a Dirac mass at ek minus of omega minus E0 multiplied by n times nu of E0, right? You look at this measure, right? That's just the measure that you obtain when you take the Dirac masses here and transport them through this scaling. Right? And what this statement says is that locally, weakly, this process, so that's a random process, xi1 of omega, right? So it depends on omega. Well, this process, xi1, converges weakly to the Poisson process. On the real line. Right? This is what this statement here says.
Excuse me?
Yes? Sure.
Kg is mj.
This is mj, yeah, thanks. You're right. Difficult to keep notations consistent. Definitely, it is mj. Thanks very much. Okay, so this is what this says. Okay, that's the second part of the theorem. Actually, these should be 3 different theorems, right? But I'm going to write it as a single one. And third, we're going to do the following thing. Look at the following quantity. You take 1 over n, and you take the number. So what you do is you look at what is called the level spacings. You take the number of j's such that the distance between the j plus first level minus or to the jth level, right, be larger than x. Okay, so I call this, what name did I give to this object? This is, well, d of, it depends of x, omega, and it depends on n, right? So it's just a level spacing. So what are we doing here? We are just, if you look at the eigenvalues, right? We look at the distance between the nearest neighbors. So this is ej plus 1 ej. We look at these distances, okay? And we just count the number of them that is above x. Well, and actually what I should do here, I should renormalize this by n. I think I forgot to renormalize this by n in my notes. Yeah, I forgot it as well in my notes. Okay, so what I do is I renormalize the distances. So I do the following thing. I take this picture. Instead of doing this shift, actually you can do it in this picture as well, because when you take the difference between ej and ej plus 1, of course, taking the shift here All right, making a shift doesn't change, right? Because you subtract the same quantity both to ej and to ej plus 1. Okay, the shift doesn't play a role. So you look at just this normalized distance. So this is just counting. You multiply this picture by n, and you're counting the distance between consecutive numbers. And you count the number of eigenvalues, which up to this, so I can write this in the same way. This is the same thing as this, of course. You count the number of eigenvalues such that the distance from this eigenvalue to the next one be larger than x over n, right? And the statement is the following. Omega almost surely dn x omega converges when n goes to infinity to the integral, the integral over r e to the minus x nu of e de. So here, this is what is called the level spacing distribution, right? You look at nearest neighbors, nearest levels, right? And you look at the spacing between the neighbor, one level and the next level in the sequence of eigenvalues. And what you compute is, what is the proportion, asymptotic proportion, of spacings that exceed x over n, right? And you get the closed formula for this, okay? Remark. What should I say? Imagine, so what is this? What is behind this? What is behind this? Remark. Imagine that you take random variables. Assume what? Assume that I call them lambda 1, lambda n are IID random variables distributed. Oh yeah, one thing I didn't say actually. According to, one thing I forgot to say here is that it's obvious from this formula, right? According to nu of E dE. From this formula here, if I take phi equals the constant function 1, what do I get? I get that this sum, well, the trice of the identity is n, divided by n, this is 1, converges to the integral of d nu e, which means that d nu, dE is the density of the probability measure, right? Integral of nu of e dE is 1. Okay, that's a probability measure. Comes directly from this formula. Just take phi equal to constant function 1. Okay, so you can take random variables that are distributed according to this probability measure. And what you get is, if you do the same thing, now you do the following, what is called, you take the ordered process. So lambda 1, lambda n, you take the values. You can write this as lambda 1 bar, or lambda n bar, right? You just order them. This is what is called the ordering of the process. So you take these values, and you order them increasingly, right? And now you can do the following. So the lambda n bar, so of course this n, this bar here, should depend on n. One doesn't write it, but it depends on n, right? It depends on omega as well. The way you order thing depends on these samples. For each sample, right, you have a reordering. But then now you can do the following thing. You can compute 1 over n to j such that lambda j plus 1 bar minus lambda j bar larger than x over n. Right? You can compute this number. And then one has that this, when n goes to infinity, converges to, well, as you imagine, dE. That is, if you take IID random variables, right, that are distributed according to nu of E, then if you do the same spacing computation as for the eigenvalues of your random Schrödinger operator, they converge to the same limit. if I take IID random variables, right, here I should have said so. If I do the same thing here, I take IID random variables here, and I do the same renormalization, right? And I compute the same probability as here, the limit is the same. So what does this say? What is the philosophy behind this? Well, for the matrix Mn of omega, right, for large n, so philosophy, and this will be behind the whole set of lectures, for large n, the random numbers or the eigenvalues, E1, En of omega, behave as if they were IID random variables distributed according to nu of E dE. Right? So taking the, so we started from this matrix, right? You take the eigenvalues. To get an eigenvalue, or to get eigenvalues from the matrix, is a highly nonlinear procedure, right? I mean, you need to solve, take the matrix minus the energy E, right, times energy, and you take the determinant, and you want E to be a root of this polynomial, right? So, of course, the roots are highly nonlinear functions. They are very complicated functions of the coefficients of the matrix. In this case, one's being fixed of the random variables, right? But nevertheless, in the limit, these random variables that you get the eigenvalues, right, behave as if, in this case, you don't take this matrix, you just take a diagonal matrix, but on the diagonal, you don't take the omega n's, what you take is IID random variables distributed according to nu of E dE, right? And this nu of E dE depends on the matrix. Right? This is something which depends on the random variables here. It's a macroscopic object, right? It's defined macroscopically. You don't need to look at things microscopically. But what you see is that the eigenvalues of your random system, this one, behave in the large system limit as if they were IID random variables. Okay? And that's the basic thing. Yes, sure.
Is it legal to think about things like decay of correlations and so on?
Exactly, sure. Of course you can. What this says is that actually the eigenvalues, right, if you think of them as numbers, depending on this variable n, they completely decorrelate. Right? They behave as if they were independent.
I mean, to measure the speed of decay of correlations and central theory.
You can give, yeah, you can measure. We're going to see. There are some estimates on the speed of decorrelation, right? There will be, I mean, the work leading to these statements, not here, but this one and that one gives some estimates on the speed of decorrelation, right? It gives some estimates on that. And you have precise estimates. Actually, you use these estimates to prove this. You have something which is actually proves a bit more than what is on the board, in the sense that, as you say, you have estimates on the speed of the correlation. Of course, one thing is that this is, here you see, if you look at the quantities that we measure, you have to take my philosophy with a grain of salt, in the sense that you look, for example, if you look at there is a stronger statement than this one that I'll state during the lectures, but I don't want to state it now, it's a bit too early. But if you look at these statements, right, for example, the one about the level spacings, you see that because you normalize the level spacing by the total number of spacings available, right, so by the size of the matrix, to get such a statement of convergence, you don't need to know all the spacings, right? You can drop any little O of n number of spacings. So it doesn't mean that all the eigenvalues actually behave like that, right? It just means that most of them Okay, you have to be careful about that. It's not that all the eigenvalues behave like that. It's just most of them that behave like that, right? And so in particular, there are some regions in energy, right? But that carry only few eigenvalues where the behavior is somewhat different, right? So you can have local behaviors that are different because these statements are only about most of the eigenvalues. And here, this statement is also weak, but in another respect. This one is also weak in another respect, in the sense that you only look at eigenvalues that are very close to some energy E0. Right? Because essentially anything that is further away than order 1 over n is just not seen by this Poisson process, because because of the scaling multiplied by n, it gets sent out to infinity. Right? So one of the difficult things, which to my knowledge was not done, and for those who attended my talk yesterday, which is required to understand what's happening to an interacting system, right? One of the difficult things is that you need to control most of the eigenvalues at the same time, right? Here, what we're going to use to prove things like this is that actually, to prove such a statement, you don't need to control all the eigenvalues at the same time, right? You just need to control large enough portions, right? Large enough fractions of these eigenvalues. Okay, so one of the goals will be to prove this actually for much more general systems. Okay, sure.
And can you calculate this function? Yes.
Not explicitly. This is dependent on the model, right? You cannot compute it explicitly for most of the models. For some models you can. For example, for the model I had on the board yesterday, right? You can compute it explicitly. And U is just, for the model I had yesterday, with the notation I used yesterday, is just this. Right? It's just so if you want, for the model I had on the board yesterday, which is, well, just as you were at the talk, right? Just assuming that you remember the function n, right? This is the relationship to the objects that I had on the board yesterday.
And does this model?
For this model, you can't compute it explicitly, as far as I know, right? As essentially, you can compute it if the probability distributions are quite special, and the uniform distribution probability, I don't think, allows any explicit computation, right? What it allows you to do is to prove, for example, that this function is positive, is always positive, right, on its support. Right? On its support, it's positive. It doesn't vanish at any point of the support. But you cannot really do an explicit computation. Okay. Well. Oh, do we have the other part as well? If not, I think I'm not gonna use this. Actually, I'm gonna use yeah, I'm gonna use this, because otherwise, once it's wet, that's going to be better. It's also faster. Okay, keep it. Yeah, and the other thing I wanted to say is that here we have some very simple special matrix, right? And what we're going to do is develop a theory that shows that actually this happens for lots of random operators in some special regime. Okay, so random Schrödinger operators. So I will assume actually that all of you are familiar with some basic probability theory and some basic spectral theory, right? I record things, but I want to make a real lecture on this, right? And the first model, so I'm going to give a few examples again. So the basic example from which all the theory started is called the Anderson model. And it's the following thing. You look at, so you're working on L2 of ZD. And then you look at the random operator minus Laplacian, so it's the discrete Laplacian, plus V omega, where minus Laplacian of the function u at the point n is just u at m for n and m distant in L1 norm by 1, right? So I drew it in 2 dimensions. Here you have n, and these are the admissible m's. Right? Okay, and well, I normalized it in this way. You can put a minus, you can remove 1/2, it depends what you want to do, but I've normalized it just in this way. And the v of omega applied to u at the point n is just the multiplication of u at n by some omega n, and I assume that omega m are random variables. So in most of the cases, I put it here in parentheses, most of the cases they're going to be assumed IID, right? But it's not really necessary. Sure.
Probably we should subtract the U.
No, you don't need to. That's a normalization. I can subtract the identity, right, times the constant to this. That's fine. But it doesn't change anything about the spectrum, right? It just shifts the spectrum. I don't need to. Okay? So I keep this one because it's simpler to write. There's less terms to write on the board, right? That's all. But of course, you can subtract the twice the dimension minus u at m at n. So I put it at n. Depends what you want to do with it, but for this purpose, that's enough. Okay, and this model actually was introduced in Anderson 58. So it's a physics paper where he actually for the first time spoke about this localized regime. So, but there are other models of interest, okay? So this is called the off-diagonal model. You can do it in higher dimensions as well. Let's do it on L2Z, right? And you define H omega by the following matrix. So it's an infinite matrix. And what you do is you take again omega n to be random variables. And on the diagonal you put 0. And you put the omega n's in such a way to have a self-adjoint or symmetric matrix off diagonal. And here's 0, right? So H omega u at n is going to be omega n minus, so let me, now I have to think actually. So I do this, so this is the un minus, let me think now. This is un plus 1 plus omega n. So at put n here, so this is omega n minus 1 un minus 1. I think this should be correct, right? So it's just the matrix is here, and if you translate it into a formula, it should be this, okay? And from the matrix, you see that's a symmetric operator, right? And what does this model? This model is the following thing. You can think of this as a model of particles, or a model of a medium. So going from n plus 1, n plus 2, oops, n plus 2. And here you have springs. And the springs are given, so this is omega n plus 1, omega n plus 2, and so on. Right? The spring strength are given by these omega n's. Okay? And in this respect, actually, these random operators are related to some random walks, right, in a random environment. So this is just the standard random walk, okay, and you add potential barriers. Right, so you can look at, for example, you can look at the standard random walk, this standard discrete random walk, and look at Feynman-Katz formulas, right, with this generator instead of the Laplacian, okay? And these are related to random walks, which are called, actually, I don't remember what the name that probabilists give to it, but roughly the probability to jump on one side and on the other side, right? So there is, let me think. No, it's not random walk actually. It's slightly more complicated than that. It's called an electrical network in one dimension, the thing. So it's also related to random walks. So there is a probabilistic aspect to the thing. If you take a general random walk in a random environment, usually what happens is that the generator of the thing is not going to be self-adjoint. Right? That's one of the, in the random case, that's one of the problems that you're going to hit. And we'll only deal with self-adjoint operators, but it's a very interesting question. I mean, there is in a way a community in mathematics which is working on random walks from probability theory, right? And on the other hand, you have people working on the spectrum of random operators. And actually these people, these two classes of people don't talk to each other very much, right? This is my experience over the last 20, 25 years, right? Since I've been working in this business. But one of the difficulties for the people that are working in the spectral theory side is that the questions that people are asking on the random walks on probability side is that it's more questions about non-self-adjoint operators, which makes, of course, spectral theory a completely different ballgame. It's much more complicated, right? Because there is no spectral resolution. It's something which is going to be much more complicated. So these are models. I'm going to speak about these models later on. And in the continuous case, on RD, there is a continuous version of the Anderson model, which is going to be the following thing. So it's, of course, going to be minus Laplacian plus V omega, where this time V omega of x is going to be just, and you fix some lattice, but actually it doesn't need to be a lattice. It can be more complicated than that. And V is some potential, right, which is assumed to be decaying fast enough at infinity for this sum to make sense. Okay, so you have a lot of choice actually. I mean, here in the choice of the model, it can depend on what situation you want to describe physically. There is another model which is, doesn't really have an analog in the discrete case, which is called, so that's the continuous Anderson model. So you may have, yeah, one thing that may be added is something in the case of the lattice, W periodic. Right, you could add a periodic potential. You don't need to add it, but you can add it, and sometimes it is useful in the sense that it's a good description for solids you want to study. And then, so these solids, actually the case when you want to study this is because you have this, you see you have ZD here. So there is some structure in these models, right? Because there is this underlying lattice that is fixed. But there are models like the Poisson model. Poisson model, which is the following. So I just described the random potential. Well, you just integrate some function against a Poisson process. Right. So what is a Poisson process? It's just a random point measure. So you mean you throw points at random, and how do you do this? You do it in the following way. Essentially, you do it in a way that if you take finitely many sets in RD, right, that are disjoint, and you count for the number of points the Poisson process puts inside these sets, right? So for each set, this is a random variable. Then because the sets are disjoint, you assume that these random variables are independent of each other, right? And the second thing, you assume that each of these random variables for a given set follows a Poisson law, the parameter of which is given by the volume of the set times a constant, which is called the intensity of the Poisson process. Right? This is what you assume. That's the basic assumption of what the Poisson process is. One way to realize it is you take in a big, you can do it as a limit using the Poisson limit theorem. You take a big cube. Inside this cube, so imagine you have a Poisson process of intensity 1. Inside this cube, you throw exactly the volume of the cube, number of IID random variables, points, distributed uniformly over the cube, right? And you let the volume of the cube go to infinity. What you get as a limit is going to be the Poisson process, right, over the whole space. Okay, so it's corresponding to the distribution of a density 1 number of points inside the whole space independently of each other, right? And uniformly over the whole space. This is what the Poisson process is. On the real line, there are other descriptions, right? If you work in one dimension, there are other descriptions like there is this time description, right? Which is the queuing line description. You just throw times of arrival inside the queue exponentially, right? Meaning that you start at time 0 and you wait for an exponential time. First person arrives, wait for another exponential time independent from the previous one. Second person arrives, and so on, right? And if you draw this, you're going to get the Poisson process over the half line. So if you shift this back to minus infinity, you get the Poisson process on the whole line. Okay, so that's another description. They are all useful. They are all for their own sake. And they were studied a lot by probabilists. So this, if you want, is something which is completely amorphous, right? This is what is called an amorphous model in the sense that there is no basic structure. There is no structure that is respected. All points are equivalent. And each of these models, to understand things about its spectrum, have their own difficulties, right? So, and the last one I want to cite actually, or describe, is the displacement model, which is somewhere in between these two. Well, what you do is you take V omega x is just the sum of Vx minus gamma minus x minus omega gamma in ZD, and here you take omega gamma to be IID valued in RD, right, and compactly supported. So it means that roughly what you're doing, instead of putting your perturbation at the point of the lattice, you are moving it away from the lattice, right, randomly. And you move it here. So this is also called dislocation models. I mean, there are a number of names for that. Okay. And, well, there are a number of common features that all these models will share. So how am I doing with time, actually? Okay, 1:45, that's fine. Okay, yeah, if anybody wants to a break, right? If you want to make a break, we can have a 5 minutes break. But if not, we just go on for time. I don't know how you feel about it. I don't know what the habits are. Right? Usually I don't do a break, but that's fine. If you want one, it's fine with me. Okay, now. So what one is interested in is the spectral theory of these models, right? Of these models. So of course, so what's the basic thing, right? For these models. So let's go back to quantum mechanics. One wants to solve the following equation, right? For any of these models, one would like to solve the following equation: I d dt of u equals h omega of u, and u at time t equals 0 equals u0. So we would like to understand what does u t look like when t goes to infinity, right? You'd like to understand what is the long time behavior of the solutions to the Schrödinger equation, which is the long time evolution of your system. Of course, by spectral theory, we're dealing with self-adjoint operators. You can solve this PDE in the following way. Well, of course you have that u of t is just e to the minus I t h omega u0, right? Just by spectral theory. As we know how to make sense of e to the minus ith, h is self-adjoint. This is why we chose to be self-adjoint. We can make sense of this. So you'd like to understand how this behaves, right? But the other step is that, well, e to the minus ith 0, omega, what is it? It is just the integral of e to the minus it lambda over the real line. And here what you should put is what is called the spectral measure of h omega. So this is also a random variable, but it's a projection valued measure, right, which is random in omega. So there are already a number of parameters in there, right? And roughly what you need to understand is integral over r zero. So that, right, is a measure which is valued in functions, right? And what you'd like to understand is how does this integral behave when time gets large, right? And of course, this is just a Fourier transform of a measure. So you can, for example, do the simpler thing, is try to measure what is happening to u of t times phi, scalar product, right? This is nothing but, so now we have a real measure, or complex valued measure, but I said, rather, scalar phi. So this is a complex valued measure. Well, and now we need to understand how does the Fourier transform of this complex valued measure behave, right, for large parameter. So there are a number of tools for that, right? You know, for example, the Riemann-Lebesgue lemma, right? There's Wiener theory. There are lots of tools, actually, and people have studied a lot what happened to the Fourier transform of a given measure, of course. But the main problem is that if you want to go along this path, you need to understand what is happening to that measure, right? You need some information about that measure. So this is why we are so interested in the spectral measure itself. We want to know what is the characteristic of the spectral measure. That's one of the basic things. And one of the basic foundings of Anderson, right? One of the basic foundings of Anderson, so for this model, so I'll keep it on the board, is the following. I'm going to draw a picture. Well, let me put a lambda here. Lambda will be positive. And let me draw a picture. Let me assume that the eigenvalues, that the random variables are IID, right? And let me assume that actually the omega m are uniform in -1, 1, on -1, 1. Well, then you can do this scaling. You have 2D, minus 2D, 2D, 0. So that's the spectrum. And that's the lambda parameter, right? And I let lambda grow from 0. So you have a slope 1 here, slope -1 here. And what you can show is that for a given lambda, we'll show that. We'll see that's not very complicated. For a given lambda, the spectrum is actually the interval going from -2D minus lambda to 2D plus lambda, right? And then there is this. So what is this? So that's the spectrum, right, for a given lambda. Well, for this given lambda, and that's conjectural, here the spectrum of h omega lambda is equal to the spectrum, the pure point spectrum. So inside this interval I, we call this inside here. I write it in this way, but it means that you intersect. You need to take the spectrum in here, so you intersect it with this interval. Lambda, and sigma continuous of h omega lambda is empty. And in here, sigma of h omega lambda is the absolutely continuous spectrum of h omega lambda, and sigma singular h omega lambda, so the union of the pure point and the discrete and the singular continuous spectrum is empty, right? Okay, that's what physicists assume to be true. So what is known, so that's conjecture of, that is conjecture, okay? That's a conjecture that this be true. What is known is this region. It is known that, I have some more chalk. Yeah? it is known that there is some region here. So in blue, you write conjecture in blue. In brown, known, there is some region here where indeed the spectrum here, all over here, is pure point, right? And that's the region, the only region that people were up to now able to, at least for this model, up to now able to analyze rigorously, right? There are models, but essentially, yeah, this is for dimension, this is what is expected. One thing I forgot, which is important. For dimension larger than 3. In dimension 1 and 2, the picture is different, right? In dimension 1, everything is known, right, for this model. It's known that the blue region does not exist. Okay, it's known that it's localized everywhere. But there were some special models, I mean, actually over different geometries that are not anymore Euclidean geometries, that are essentially tree graphs. Over tree graphs, it was proved that the blue region also exists, right? That there is some AC spectrum. This is also recent work. Actually, depending on the tree graphs, right? And well, no, actually, the initial work on the Cayley tree is not that recent. It must be something like still 20 years old. Yeah, this must be some 20 years old. But to determine exactly the phase diagram, meaning what the graph is like, this was done recently, over the last 3 years, I think. It's work by Eisman and Warzer. So we will be exclusively known, which is called the localized region. And we will work exclusively, and I'll be only dealing with this region, right, for the spectrum of my operators. So I drew the picture, the phase portrait, in the case of the Anderson model. There are similar pictures for the other models, right? But actually for the other models, this model, the Anderson model, is the one that has been studied the most, right? So this is the one for which there are the most results. For the other models, the continuous Anderson model has been studied a lot, but there are still much less results than for this one. Much less things are known, right? And for the Poisson model, even less things are known, but the localized region, I mean, localized region has been proved for all the models actually I put on the board up to now. The existence of some localized region, not the characterization of exactly what it is, right? And of course, the characterization of this blue region does not exist for any model except on the trees, except on trees. Yeah.
What does it mean from the physicist point of view? That if lambda is big, you have only pure point spectrum?
No, yeah, exactly. What does it mean? It means the following thing. So the lambda here and the lambda there is not the same. But here, imagine that you have pure point spectrum. It means that this measure here is just a set of Dirac masses, right? But then what you can prove, it's not true completely in general, right? This is what I'm going to say now is going to be true for the models, but it's not true for a general operator that just has this pure point spectrum, right? Because it's not, this measure is not only determined by the spectrum, it's also determined by the nature of the eigenfunctions in case you're dealing with point spectrum, right? Or the generalized eigenfunctions in case you're dealing with continuous spectrum, right? But if the eigenfunctions, because what happens is that in this localized regime, yeah, one thing I said is was pure point, but there was another thing. In the localized region, what you have is that the eigenfunctions decay exponentially. And actually, they decay exponentially at infinity, right? And in a rather strong way. Because decaying exponentially is not much per se either. You need something like uniformity conditions, right? Of course, it cannot be completely uniform. This has been proved. But you need something like some uniform conditions. But once you have this exponential decay, what you can show is that for this pure point spectrum, right? Well, what happens is that you are not going, if you look, for example, at an observables like this, you look at, so you have u of t and x, right? So x here is n, as we're dealing with a discrete model, it's n, and you are looking at this, and you sum, so you sum over all n in ZD, right? So what you're looking at the expected value of the distance to the origin applied to the evolution to your initial state u0, right? What you can show is that, imagine that the u0, right, by the operator would be transformed in a wave packet that travels, right, that goes around. What would happen? It would happen that as time goes on, the ends that this function sees would become larger and larger. So this would go to infinity, right? If you have, imagine that the evolution, the effect of the evolution, the effect of applying the Schrödinger semigroup to your wave packet is that it moves the wave packet inside space, right, away from the origin, then this would mean that these numbers, if you look at this measure, so this sum is equal to 1, right? So this is a measure on the integer zd. It would mean that the support of this measure goes off to infinity. But it would mean that then this weighted sum grows when t grows. But in the localized regime, one thing that was proven is that, well, I don't have enough space here, but I'll write it here. The sup over time is finite of this. It means that the wave packets are frozen, right? Wave packets don't move to infinity. And that's what happens in the localized regime. In the delocalized regime, what is mathematically a conjecture for physicists, it's a result that they are sure of, okay? But for physicists, what happens in the delocalized regime is that this grows quadratically with time, right? So it means that roughly u, the support of utn, when time evolves, moves linearly with time, right? And the linear constant is called the diffusion constant. And that's the difference between these two regions. In this region, you have electricity conduction. Your sample is a conductor. Electricity, actually, the electrons move inside the solid once you apply tension on both sides. In this region, they don't, if the tension is not high enough, right? So physically, it's a very basic phenomenon. Of course, it's quite complicated because here we have a model which is a single electron inside this medium, right? If you really look at electricity conduction, you need many electrons, right? You need to resort to models like the one I had yesterday on the blackboard. And there, the picture, even for physicists, is not clear at all. I mean, they don't agree with each other about what is the truth or not, okay? And so, but for the one particle picture, if you imagine that the movement of one particle is exactly, if you neglect interactions if you want, right? What they are going to tell you is that in this region, in this energy region, your material behaves like an insulator, right? Whereas in this energy region, it's going to behave like a conductor, right? So does this answer your question? Yeah. Okay. So what was I saying for that? Okay, so we are going to restrict ourselves to this region. It's the only region where actually I know of mathematical statements. Of course, in these models, you can throw things in, and people have studied lots of random operators, right? You can throw in random magnetic fields, you can throw in a constant magnetic field, you can do many other things, okay? But the basic philosophies and ideas that were developed to study these will be essentially explained on these simple models. Okay, so let's start with chapter 1. So this was just a brief introduction. So, ergodic operators. Okay, so we're going to give ourselves, let's take a probability space with a sigma algebra and some probability measure, right? And we give ourselves a mapping. Let's call it H omega. This is a self-adjoint operator on some Hilbert space H. Right, so I don't specify the domain, but what I'm going, so pick a mapping like this. I don't specify the domain, but what I'm going to assume is the following, such that, well, if you look at, so I want it to be self-adjoint on H. So here, right, of course, it could be unbounded. Okay, so I need a domain, but I don't want to speak about the domain for the moment. But what I'm going to do to prevent speaking from domain is the following thing. For Z complex, not real, if I look at the map, so this we know because it's self-adjoint, this we know is a bound operator, right? That's a nice bound operator. I assume that the map that to omega associates the resolvent of H omega at Z is measurable, right? So I just want what is called measurable. So because these are bound operators, right? So this, we know what measurable means, right? Here we have bound operators. So the bounded operators are, because you're looking at the operator norm, are endowed with some topology. From this topology, you construct Borelian sets, right? Which gives you a measurable structure on the bounded operators. And then what you ask for is that the mapping, sending omega to this resolvent, maps, inverse maps, Borelian sets in the bound operators to Borelian sets in H omega. In particular, if you have some continuity with respect to omega, right? If you can realize this random process as, or this random operator, like in my examples, right? You had an explicit dependence on random variables. If this is continuous, then it's going to be measurable, right? Because the inverse image of some open set is going to be open, so it's going to be Borelian, and then using the usual set theory nonsense, right? You're going to get that this is measurable. So one of the important things is that measurable here, you can do it in the norm sense as I did, but you can also consider other topologies on bound operators. You can consider the strong topology, right? Which is just you take as semi-norms the bound operator applied to any vector, and this gives you a family of semi-norms, right? And of course, because the operators are bounded, you can actually take a countable family of semi-norms, which is given by just, we are dealing, yeah, the Hilbert space H here is assumed to be separable. So it has a countable family that is dense, right? It admits a countable dense subset. Okay, this is what I mean by separable. Okay, it's not the Hausdorff separability for topology. Right? And so what is happening is that measurability can be measured for norm topology, right? Or the Borelians created by norm topology, but also by the strong topology, right? Meaning that you look at the semi-norms operator applied to some vector in norm, but also by the weak topology, which means that you look at the semi-norms operator applied to phi scalar psi. Right? And the important thing is that when you speak of measurability, all three things are the same. You don't need to care about, right? Norm measurable, strong measurable, weak measurable gives you the same set of objects. Right? There's no difference. Right? So we can always look at weak measurable. Okay. So in particular, well, the only thing we need to assume, what does it mean? It means that if you look at this is equivalent to say that for any phi psi in H, for any Z that is not real, this is in C minus, I forgot to. Well, omega phi Z minus H omega inverse psi is measurable, and this one complex valued. Right? This is complex valued, and we assume that this is measurable. It's the same thing. And one of the basic properties is the following thing. Now, in the title there is the name ergodic, right? So I need to recall what is an ergodic transformation. So assume, let me just recall this one. Okay. Pick T equals Tj for Jj, where Tj goes from omega to omega, right, is a measure preserving. So this is measurable in the sense that you look at the sigma algebra A here and the same here. measure preserving transformation. Right, what does it mean? It means that if you look at Tj inverse P, this is P, right? It just preserves the measure. So if another way to say this, the P of Tja is P of A. Right, this is the probability that I put. I just assume that it's measure preserving. Okay, and what I'm going to assume, then we say that this thing is ergodic. So T, so definition, T is ergodic. So this set is ergodic if and only if one has the following thing. If A belongs, it's an event in the sigma algebra. To say that what? To say that Tj of A, right? Tj of A is equal to A for any j is the same thing, or is the same thing as to say that P of A is 0 or 1. Okay, the only sets that are invariant or all the transformation I have here are sets that have total measure or zero measure. Right? So essentially it's the whole space or the empty set.
Probably.
Yeah, here I have to take this because otherwise I need it to invertible.
I mean, it's.
Yeah, this is up to sets of measure 0 as usual.
Mod 0.
This is mod 0. Yeah, sure. This is sure. Sure. This is. Let me write this. This is. Well, let me do it this. Tn delta A equals 0. Right. Take the symmetric difference. Take probability equals 0. So here we're happy. That is exactly. It's mod sets of measure 0. Definitely. And it's the same thing. It's the same thing as to say that if x, well, no. You can rephrase it in terms of random variables, right? If you take any measurable mapping from omega to some probability space, you ask that the only maps that are invariant, right, are the constants. Okay? And now we will say that an operator, so definition, the operator H omega, so the family is ergodic if and only if there exists an ergodic family of transformations and U a set of unitary transform on H such that, well, H T J omega can actually be realized as Uj star H omega Uj. Meaning you can realize the shift, right? It's not really a shift, but the transformation of omega by Tj by some unitary transform on the Hilbert space. Okay? So, example. Take the Anderson model. Well, actually I do it with continuous Anderson. On L2RD, right? H omega is minus Laplacian plus sum of omega gamma V x minus gamma, gamma in ZD. And assume that, let's say V is C0 with compact support on RD. Then of course, it's easy to see that the mapping Z maps to Z minus H omega inverse, right? The thing is actually continuous, sorry, that's omega maps to, this is actually continuous. So omega gammas are IID, right? You can check that this phi psi, this mapping here, this is easy to check that this thing is actually continuous in all the random variables, right? Because so this is IID, so you can actually realize, these IID on the probability space omega is just R to the ZD, right? The sigma algebra is just what is called the cylinders, the sigma algebra generated by the cylinders. Right? What this means as the cylinders, it means that you take a number of random variables for which you take a Borelian, and all the others, they are just RD, right? And you take the sigma algebra generated by this set. And here the probability measure is just the product measure of some distribution, d mu, which is the individual distribution given for each omega, right? And then it's easy to check that this is actually continuous. So from, right, from R to ZD, that this is actually a continuous. Actually, to make it really simple, let's take it here from some, let's take a compact set. Let's do it from some compact set. Assume that they are bounded. Otherwise, you always have the problem. It's a bit more complicated, but it still works, right? You can do it in the same way, but you hit into some technical difficulties, right? But it's still working. You just do it by some limiting procedure. Okay, you just truncate the thing. Once you have done it for compact sets, right? You can do it for which topology?
What topology?
Well, on this side, it's just the complex numbers, right? And on this side, well, you take what do you take? You just take the topology, which is, you take the cylinders, right? And you take open set and the cylinders, and you just take the topology that's generated by that, right? So meaning that outside of the cylinder, I mean, it's not going to be, the whole real line is going to be K, this compact set, right? Just take this topology. You can actually do something stronger than that. Just using the, I mean, when you want to compare, right, you just use the resolvent formula and standard decay estimates because Z is complex, okay? And I think here you can take something like, let me think now, soup norm, right? You just take the soup over the sequences, take the soup norm here, the soup topology is going to be fine. Sure. To this?
Family of TJ, T psi. I mean.
Here? These are measurable.
Yes.
But yeah, these are by definition they are measurable because they're measure preserving, so you need them to be measurable.
No, I mean with respect to psi, to this parameter.
Which psi? I'm sorry.
J.
Oh, no. It's just a family. I mean, I just take any.
Maybe countable.
Well, in the examples, it's going to be countable, but I'm not sure you really need it.
I mean, there could be some issues with sets of measure 0 if we don't assume measurability or count.
Ah, I see what you mean. Okay, you're right. Let's take it countable. You're right, definitely. No, you're right. You're right, because otherwise I need to assume something stronger than this. I need to assume, you're right. Countable is fine, yeah. It will be, so J countable. You're definitely right. In all the examples, it's going to be countable, but actually, no, well, yeah. In the examples, it's not always going to be countable, but it's going to be, as you said, overcome by some continuity properties, right? But in this case, yeah, we take it countable is fine. We just take it countable, that's fine. Okay, for the thing, so here, so the measurability is then given by these simple properties. And what is the sets? What are the Tj? Well, Tj of some, so for J in ZD, Tj of some sequence omega at gamma is just going to be omega, sorry, I'll use the indices, shifted by J, right? So you just do the shift by J, right, on the sequence of random variables omega gamma. And then it is well known that the product measure, right, well, admits the shifts as an ergodic group, right? This is ergodic, so this family is ergodic. This is just the 0, 1 law, right? If you take one dimension, if you take it in one dimension, it's just the 0, 1 law. Okay, so roughly, hand-waving argument, which is not correct mathematically, is the following thing. Imagine that you have some set which is invariant by all the shifts. What does it mean? It means that roughly it's going to be a cube, right? Your set, because it's invariant by all the shifts, your set should roughly be a cube. But if you take a cube with infinitely many sides, right? Well, either the side is measure 1, in which case the measure of the cube is 1, or the side is measure less than 1, in case the infinite power of something less than 1 is going to be 0. Right? So that's the hand waving. It's not correct mathematically, right? I mean, this is not the correct proof. But it's nevertheless the basic philosophy behind it, right? This is what's happening. Okay. So in this case, we have an ergodic operator, right? And the first basic property for ergodic operators is that, well, the spectral data, actually the spectrum of an ergodic operator is not going to depend on omega. So the proof of this is the following. So let me prove the following proposition. Let P omega be an ergodic family of self-adjoint projectors. Right. So we take an ergodic family of self-adjoint projectors, and then what does one have then? Omega, almost surely, the rank of P omega, which is also the trace of P omega, is constant. Right? They share the same trace, they share the same rank. Right? The projector, because they are projectors, trace and rank are the same things. Okay. Okay, but let's prove this. Right? So proof. Well, let's look at. So the trace of P omega, of course, is valued. This is valued in 0 plus infinity, right? It can be infinite. Okay, actually, in most of the cases, for most of the cases we are going to deal with, this is going to be infinite. Okay, and the important thing is the following: is that, well, the only thing that you need is that this be measurable. Right? You want this object be measurable. And how do you define it? Well, it's just if you take an orthonormal basis, it's just going to be the sum of phi j P omega phi j larger than 1, right? So because all of these are measurable, the sum is going to be measurable again. Okay, so you get measurability of this. But ergodicity tells us the following thing. It tells us that the trace of what? Of P of Tj omega is going to be the trace of Uj star P omega Uj. But this is, of course, the trace of P omega. The trace is invariant under unitary transformations, right? And so what you have a random variable which is invariant under this ergodic family. So this is almost surely constant by ergodicity. Okay. Okay. And from this, we're going to get the first theorem, which is actually due to Leonid Pasteur. It's early 80s. Let H omega be an ergodic operator family. Then there exists sigma, a subset of R closed, such that omega almost surely, the spectrum of H omega is sigma. So even though you have this big family of operators, they all have the same spectrum. Right? This is why one speaks of a single random operator, right? Because they have something really in common. So the proof essentially boils down to let delta be is an interval, right? And I define E delta of omega. This is just a spectral projector on the interval delta of H omega, also a spectral. On of H omega. Okay, and what happens? So, of course, E delta Tj omega is going to be, well, what do I want to say? No, this is this. Okay. I need one more thing here. Let me think now. Tac, tac, tac. Okay. Oh yeah. Okay, so this is going to be, well, okay, right, that's fine. So what I get is that this is a family, right? I get that E delta omega is, well, I almost get that, I don't get it quite yet, is ergodic if the one thing that is missing, it is measurable, right? I don't know that the thing is measurable yet. That's the thing I'm missing. Okay? I don't know. I mean, here I have some complicated function of an operator, right? The spectral projector. This computation is correct. That's not a problem. The problem is this function still measurable, right? And it is going to be just by approximation. For example, what can I do? Well, I can do it first for delta compact. Let's say, right? I do it for delta compact. And what I can do is to show measurability. So I approximate So what should I do? Let me think. One delta. So well, I can do this at least for bounded operators. That's going to work for bounded operators by polynomials. And this is okay. This is okay if h omega is bounded. Well, bounded if meaning the following thing. It means that the family, right? The family is bounded, meaning that the spectrum of all these operators belongs to a compact set. If the spectrum of all these operators belongs to one and the same compact set, right? Then what you can do is that on this compact set, you can approximate this characteristic function, right? By a sequence of polynomials. Of course, outside the compact set, the polynomials are going to do what they want, right? You don't control them outside. But inside this compact set, you can control the distance to this by the polynomials, right? And the polynomials of the h omegas are going to be measurable because they're just going to be composition of a continuous function with a measurable function, right? So they're going to be measurable. And so this way you can get that this, if the whole family, right, altogether is bounded, you're going to get that these operators, right, are measurable. The E delta omega are going to be measurable projections. Let me think now for a moment, what do I do if I, yeah, so this is for example, it applies to the Anderson model. What should I do in general if I don't have a bounded operator? I guess I'm going to resort again to resolvent, right? So this is okay if, oh, yes. If not, what you can do is the following thing. Well, let me think now. So there is, now I don't remember the name of the formula. What you can show is that if you have omega 1 over 2. This is the limit of the integral over control gamma that I'm going to draw when epsilon goes to 0 of z minus h omega minus 1 dz. And gamma is the following contour. So I have A, B, this is just Stone's formula, right? This is called Stone's formula now. Name, right? Okay. So what do I get? I get that this thing now, this function is measurable. Because sorry, did I forget something? No, that's correct. That's correct. That's an operator, right? Maybe 1 over 2 pi. Maybe 1 over 2 pi somewhere. Right.
We always talk about bounded operators.
No. Here I talk about any operators. That's still correct if I take a self-adjoint unbounded operator. This formula is still correct. Right? For boundeds, you can use polynomials. For bounded operators, you can use polynomials. But this formula is still correct if you take unbounded. Right? As long as self-adjoint. I don't remember. No, maybe it's 1 over pi. It's not 2 pi. It's 1 over pi. Right?
About,
so this is I mean, let me write it. It's integral from A to B of 1 over x minus I epsilon minus h omega minus 1 over x plus I epsilon minus h omega dx. Right? So if you rewrite it using the spectral measure, it's going to be 1 over pi integral against the spectral measure, d lambda, from from a to b over r of what? Of 1 over x minus I epsilon minus lambda. So if I take, so this is just, let me have, so I have 2, so this is x minus lambda squared minus plus epsilon squared, and I have, because of this, 2I epsilon, so there's an I missing somewhere, dx, right? And this is, if you want, just the E lambda, right? This is just this. Okay, 1 over I, there may be 2I then. Up here we're going to get it. So this goes away, this goes away. And now you see that this function, right, it converges if x is between a, if lambda is between a and b, it's going to converge to the integral of 1 over plus 1 over x squared, right? Which is pi divided by pi makes 1. If x is equal to a, you just get half of the integral. And if f is equal to b, you get half of the integral. And if x is outside, you get it converged to 0, right? And so you get this converges. So it's 1 over 2 pi I. Right, it's just Cauchy formula. So up to, okay, that's Stone's formula. So this tells us that this thing now is measurable, right? And now, from this, you'd be happy you get any interval if you can get that the spectral project on a point is measurable, right? But to get the spectral project on a point, what you do is you just let A and B shrink, go to a point, right? You let A and B take a point C, you let A and B shrink, A from above, from below, B from above, and you get measurability of the spectral projector on the point by just, again, a limiting procedure, right? And once you have it for point, you can remove the endpoints and you get it for an open set and for a closed set, and you get it for everybody, right? You get this way, you get spectral measurability of on any open set. And then you go from open to Borel by the usual probabilistic argument, right? You just need it on open sets. So Stone's formula does it for us. So we know that the thing is measurable. So in particular, what we know is that we know the following thing. So we know that the rank of E delta omega is constant, equals to, I don't know, R of delta, omega almost surely. Right? Okay. So let me think now. What is the spectrum? Spectrum of H, of H omega. All right, what is the spectrum of H omega? I'm going to express this in terms of the operator. Well, it's the set of points E such that for any epsilon positive, right, or for any n positive, the rank of E minus, I call it lambda. Lambda minus 1 over n, lambda plus 1 over n, for example, the open sets, right, is positive. And this is a spectrum, right? The spectrum is just the set of real numbers such that if you look at the spectral projector on this small interval, any interval as small as you like around centered in this point, you get something which has positive rank, right, in the spectrum. So, I just need, I'm annoyed just by one more thing, right, is that I have too many lambdas at hand, okay? So what I'm going to do is I'm going to look at the following thing. I'm going to look at the rational points, right, that are inside the spectrum, roughly. So what's the right way to do that? Let me check what I wrote. Oh yeah. Let me think.
Maybe you can call the set as just intersections with direct influences.
Yeah, you can, well, many ways. I just want something simple. Let me think now. Okay, what I'm going to do is the following thing. Let's look at the complementary of the spectrum, right? This is going to be the union of PQ rational such that, I write something, we check whether it's correct. So it's the union over what? Over the PQ rational numbers such that E omega interval PQ, so I take P less than Q, P less than Q, such that the projector, the rank of the projector on the interval PQ, omega, is 0, right? I take the complementary spectrum as an open set should be simpler to work with, right? And what I'm saying is that
maybe open set PQ.
Well, it doesn't change. You can take it open. That's fine, but it's going to be the same thing. Because if you take it closed, it just means that you come from inside and you enlarge it, right? But it's going to be the same thing. Okay? So you just take the set of the union of all intervals of the form PQ, right? P and Q rational, such that the rank of this is 0. Right? This gives you the spectrum, the complementary of the spectrum. Right? But now, what do we know? We know that if you call omega PQ, right, it's the set of omegas such that the rank of EPQ of omega is equal to 0. Well, we know that this probability of omega, because this is ergodic projector, this is either 0 or 1. Either almost surely, right? Either almost surely the rank of, the rank of EPQ of omega is equal to 0, or almost surely it's different from 0 because it's almost surely constant, right? So it's either almost surely equal to 0 or almost surely different from 0. And then what I do is what I'm going to take, what I want to take is I want to take now, let me think now, to think. I'm almost there. Well, I want to take the omega is the intersection over P less than Q, PQ rational, such that omega PQ has measure 1. Right? Of omega PQ. This thing has total measure. Right? Because it's a countable intersection now. And what I want to show is that if for omega 1 and omega 2 in omega, I want to show that the complementaries of the spectrum are the same. Right? So I want to show right? What I want is this. If I prove this, I'm finished. I have shown that on this set of full measure, right, the complementaries of the spectrum are the same, so the spectra are the same. Okay. So, what do I need to do for this? Okay, so for what we know is that as omega 1 and omega 2 as well belongs to omega, for all p less than q, P Q in Q squared, we have that what? We have that, yeah, for omega, as omega 2 and omega 1 are the same, right? We have that the rank of E PQ omega 1 is equal to the rank of E PQ omega 2. Right? By definition. Because they all belong to omega, to this intersection, the two ranks are the same. But then, look at this. Right? The two ranks being the same, it means that the complementaries of the spectra are the same. Right? This implies
that these ranks can be different if they are not zero.
Oh yeah, you're right. Yeah, you're right. I should. Let me think. No, you're right. Let me think now. No, it's not that the ranks are the same. You're right. It's not that the ranks are the same. Let me think. How should I phrase it? You're right. It's not that the ranks are the same if they are zero, right? And if they're different, some could. You're right. Some could be. Let me think. Not that the ranks are the same. How should I write it? I don't want to put too many quantifiers. Let me think. Yeah, the only way to write it is this, right? This is 0 is equivalent to that is 0, right? That's the only way to write it, okay? If one of the ranks is equal to 0, then the other one has to be 0 as well, okay? You're right, it's not that the ranks are equal. In case they are non-zero, they could be different, right? And so the two complementaries of the spectra are the same, so the two spectra are the same, okay? And we get the first thing. So how late is it? Oh, there is a watch here. Okay. So at what time? Oh, yeah, I'm already way past my time, actually. I'm sorry. Well, we'll stop here. Thanks.
Okay.